on and bring our next speaker, Hamidreza Abbaspour from University of Southern California. And he'll be talking about neural dynamics underlying naturalistic reach and grasp movements. The floor is yours, Hamidreza. We cannot hear you.
Sorry, I was muted. Hello, everyone. Happy to be here. In this talk, I will be talking about the multi-scale low-dimensional dynamics during naturalistic reach and grasp movements. There have been significant advances on our understanding of motor cortical dynamics and how low-dimensional dynamics during neural population activity explain movements. In this talk, we would like to extend prior dynamical models in two directions. First of all, prior dynamical models have mainly analyzed spiking population activity to extract low-dimensional dynamics. However, we know that behavior is encoded across multiple spatiotemporal scales of brain activity, ranging from small scale processes represented in spiking of neurons to larger scale brain networks reflected in field signals such as local field potentials, LFPs. Therefore, we want to build neural dynamical models that are multi-scale and extract low-dimensional dynamics from combined spiking and LFP activity and compare them. Also, while some prior works have looked at decoding accuracy during naturalistic reach and grasp movements, the low-dimensional dynamics of population activity are relatively underexplored compared to some other conventional tasks. Therefore, we want to also understand and study, investigate the low-dimensional dynamics during naturalistic reach and grasp movements. Extracting low-dimensional dynamics from a combined spiking and LFP activity is challenging because these signals have different statistical profiles and timescales. Local field potentials are continuous and they have slower timescales compared to spikes, which are discrete, and we model them with binary spike events given their fast time scale and their biophysiological properties. We solved this challenge by building a multi-scale state space model in which the state evolves in time with linear state equations, and we model field signals and binary spikes given their statistical profiles. For example, if you look at the equations here, the first two equations give you the famous linear state space model, but the challenge is how do we also add the spikings that are related with the same latent state, and we add the third equation. We can then relate the behavior by a linear projections of these latent states, which are low-dimensional representation of the combined population activity. So the parameters of this model need to be learned with a machine learning method. We developed this multi-scale expectation maximization algorithm, which identifies all the model parameters in the presence of the latent state. I'm not going to go through the details of the algorithm. You can find the math in our prior work in 2019. So after having this multi-scale EM, we can now learn low-dimensional dynamics with spiking population activity, local field potential network activity, and also the combined version of them. And we can investigate the dynamical characteristics of the low-dimensional dynamics. But how do we investigate the dynamical characteristics? To do that, we take a close look at the state transition matrix in the state space equation. The eigenvalues of the state transition matrix directly and uniquely quantify two dynamical characteristics, the time decay and the oscillation frequency. The time decay is how fast the latent state decay in time given the response to an impulse response. And the time decay directly depends on the radius of the eigenvalue on the unit circle. Also, the oscillation frequency is how fast the latent state oscillates in time given an impulse response. Also, the frequency depends on the angle of eigenvalue on the unit circle. So since the state here is latent, we don't know what the state dimension is, and we don't know which eigenvalues in the state space are important. We have to have a way to distinguish the important eigenvalue of network dynamics from the ones that are not very important. Therefore, what we do and what we argue is that the eigenvalues that are important in network dynamics should appear persistently regardless of what state dimension the latent states are identified from. For example, we what we do, we extract the eigenvalues from latent state space models from different dimensions. We put them all on top of each other, and the eigenvalues that appear persistent regardless of the state dimensions are the important eigenvalues of the network dynamics. For example, in these plots, the vertical clusters mean the eigenvalues that are persistently present in the state space models regardless of what state dimension we identify the model with. We call this diagram the eigenvalue dimension diagram, and we look for the vertical clusters on the eigenvalue dimension diagram. The vertical clusters are important modes of the system, and we call them principal dynamical modes of the system. And also, I discussed that we want to understand the low-dimensional dynamics during naturalistic reach and grasp movement. What we do, we look at this naturalistic reach and grasp movement test performed by our collaborators at Bijan Pesharon Lab at New York University. In this task, there were no specific go cues or hold cues that would isolate any part of the movement. Monkeys naturalistically performed the task to diverse 3D locations in front of them, and the task was continuously performed, and there were no trial structure. And more than 100 channels of spike and LFP were recorded from premotor, prefrontal, and motor areas. And we also tracked the 27 joint angles on the arm and fingers as the behavior during this task. So now that we have these tools, what questions we want to answer? We want to understand how small-scale spiking network activity and larger-scale LFP network activity relate to each other in controlling movement, and how do they explain naturalistic movement. So what we do, we perform the multi-scale state-space modeling on spiking population activity, LFP population activity, and the combined activity of them. And we looked at the eigenvalues or the dynamical modes of the system. First of all, we observed that there existed several dynamical modes in the spiking population activity. As you see in this plot, the vertical cluster represents the dynamical modes that I just discussed. And we can see that the dynamical modes are located very dense around the centroid cluster, meaning they had persistent dynamical characteristics across the state dimension. That means that the dynamical characteristics of the dynamical modes are preserved across state dimensions. Then the question is, by the way, each of these clusters are represented by one color in this diagram. Then the next question is which dynamical mode was most predictive of the behavior? So what we did, we quantified the prediction accuracy of each of these dynamical modes or dynamical latent state modes. We calculated the prediction accuracy. And interestingly, in spiking network activity, one of them was dominantly predictive of behavior. We repeated the same analysis with LFP network activity. Again, we observed several dynamical modes in the LFP network activity. And interestingly, again, one of the modes were dominantly predictive of behavior. So this takes us to this question that now that we get this dominant mode in spiking network activity and LFP network activity, do they have any relationship with each other or not? Or are they separate? So interestingly, even though there were several distinct modes in both population activities, the one mode that predicted behavior dominantly had similar eigenvalue in both scales, and meaning it had similar dynamical characteristics, therefore similar time decay and oscillation frequencies. Therefore, we call this predictive mode that is shared between both of the scales the multi-scale predictive mode. Then the first question we had was, maybe this multi-scale predictive mode is shared between spiking and LFP network activity just because they are simply replicating behavior modes. So what we did, we did the same model analysis on the behavior time series, and we observed that the behavior modes had significantly larger time decays compared to the multi-scale predictive mode, and also they had significantly wider frequencies. So the multi-scale predictive mode was not shared between spiking and LFP network activity just because they simply replicated the behavior mode. Also, we wanted to see, we argued that if the multi-scale predictive mode was actually multi-scale, if we combine spiking network activity and LFP network activity and learn to unify the state space model, do we identify if we identify the same mode at the same location, it means it was really shared. So it would identify the same mode with the same dynamical characteristics at the same location. And indeed, when we learned a low-dimensional dynamics from combined spiking and LFP network activity, we observed that the same dynamical mode was identified at the same location. This further validates the fact that the multiscale predictive mode was actually multiscale. Also, the multiscale predictive mode was not only shared between spiking and LFP network activity, it was also shared across animals, meaning even though the animals performed the naturalistic reach and grasp voluntarily and they opted for different strategies to perform the task, the multiscale predictive mode had similar dynamical characteristics across them. And this again further validates the fact that this multiscale predictive mode explains naturalistic reach and grasp behavior. The time decay of the multiscale predictive mode was 1 second, and the frequency of it was around 0.2 hertz. We then questioned whether, because we identified many dynamical modes across experimental sessions on animals with this and scales with the same dynamical characteristics, meaning decay frequency characteristics. We then questioned, are both of these dynamical characteristics important in explaining behavior prediction accuracies? And we first looked at the decay values of the
Hamidreza, you have 1 minute left.
We looked at the decay values of the multiscale predictive mode, and we observed that the multiscale predictive mode indeed have larger time decays compared to other principal modes. Also, we built a multivariate linear regression model from the decay and frequency characteristics of the multiscale predictive mode and other principal mode to the prediction accuracy. And indeed, we observed that both of these dynamical characteristics had significant contribution to the prediction accuracy. Therefore, both are important in explaining naturalistic behavior. In summary, we observed a shared mode in spiking and LFP network activity and animals. Therefore, this mode was completely multiscale and it was predictive of behavior, therefore a multiscale predictive mode. This mode explained naturalistic behavior, and also we propose that this is due to the integrated action of large-scale brain networks. Both decay and frequency characteristics of the multiscale predictive mode explain naturalistic behavior. The 1 second time decay indicated that naturalistic behavior relied on integrating dynamics over longer time periods compared to the other modes. And also the 0.2 hertz frequency quantified the rotational frequency of the network dynamics. I would like to thank all my friends and my advisor Mariam at Shawnee Lab, our collaborators, in particular Bijan Pesaran, and all our funding sources. And with that in mind, I would be happy to take any questions. Thank you.
Thanks for the wonderful talk. We have a question open from Julian Block. Is it possible you're getting eigenvalues that are consistent across different dimensions, but correspond to different spatial modes? That is, same frequency and decay, but explaining completely different dynamics.
Can you repeat the question? Because my internet just cut out.
Okay. So the question is it possible you're getting eigenvalues that are consistent across the dimensions, but which correspond to different spatial modes? That is, same frequency and decay, but explaining completely different dynamics across different dimensions.
So if an eigenvalue has same dynamical, it has same decay frequency characteristic, meaning it has a same location on the unit circle. I'm not sure what the question, I'm not sure what they mean by spatial mode, but if the eigenvalue is located at a specific frequency, the dynamical characteristics of the latent state correspond to it is uniquely determined. So they can't have different dynamics given the same eigenvalue. So same eigenvalue would always result in same flow field dynamics, therefore similar dynamics in time. The only difference in dynamical system is the initial condition, but the dynamical characteristics will be similar.
Okay, great. As we are waiting for maybe more questions, I have where are you going to take this result? Like what are the next steps?
So first of all, since we observed that the information in naturalistic behavior is multi-scale, we can take advantage of it for near future neurotechnology. So when we want to build brain-machine interfaces, we could take advantage of local field potentials given the durability compared to sparks, which degrade over time. So one obvious advantage is we can use local field potential signals in future BCIs. And also it gives us the knowledge of the fact that the information is also there in larger scale brain networks such as local field potential.
Okay, great. That's really interesting.
Thank you.
So if we have no more questions, I think we can wrap up the session.